Hey everyone, welcome back to Calculus 2. This is lecture 17 of the course, and in this one we're going to talk about trigonometric integrals. This is going to be a continuation of the methods that we're developing for dealing with more complicated functions and trying to integrate them. And so in this section we're going to look at situations where we have sine and cosines combinations as well as secant and tangent combinations. And so let's jump into that. We're going to call this section 3.3 trigonometric integrals. All right. Now, the kinds of integrals that we're going to be interested in, as I said, are going to be integrals that are combinations of sine and cosine, so things like this: sine to the m of x, cos to the n of x, dx, where m is some exponent, n is some exponent. Or, things like this, where you've got secant raised to some power times the tangent raised to some power. Okay, and these are just the two forms that we're going to study in this section. These same methods can be employed more broadly, but we're going to kind of stick to these as our main examples. And just know that these methods that we're going to develop can be extended to other combinations of trig functions as well, potentially, right? With some slight modification of the method. But basically, what we're going to be doing is integrating these types of functions by breaking them into combinations of trig integrals for which we can apply basically the power rule, with the basic U substitution kind of thing. So let's take an example here, just a motivating example, I suppose, and then we'll get into the nuts and bolts of this. So to evaluate something like the integral of sine to the 5th power x cosine of x dx. We can use like a U substitution, right? We can let U equal the sine of x, then du is equal to the cosine of x, cosine of x dx, right? So we get, the integral of sine of x to the 5th cos x dx is equal to the integral of u to the 5th du, right? And so we can quickly see that that's u to the 6th over 6 plus c, and so that means it's 1/6 sine to the 6th power of x plus c, right? And so in this example, it's very beneficial that we have sine raised to some power, and then we happen to have a single cosine here, right? Because if we choose u to be equal to sine, then we know du is going to be equal to cosine x dx, right? And so it's handy to have that built into the integrand. And so what we're going to do is kind of play on this sort of phenomenon where you have both the u and the du handily given to you, right? In this case, it was given to us. But what we're going to do is we're going to use trig identities, some very common trig identities, to convert integrals into a form where we have the u and the du ready to go. Okay. Now, this strategy is, it's going to seem a little convoluted. Unfortunately, it's just kind of the way it is. A lot of these trigonometric integrals can be they're just complex, and any attempt to really make them super straightforward is inevitably going to involve a lot of guidelines and steps, and unfortunately that's kind of the way it is here too. But I do think my intention is to kind of go through it in detail and show you exactly how it works on a handful of examples, and then you'll be able to take that experience and apply it to even greater combinations. So just a quick review. There's going to be a couple of trig identities that we'll need for this. So I'll just write important trig identities. There's only a handful here. These are things you've definitely seen before, certainly if you took like a pre-calculus or a trigonometry course. So the first one is just the Pythagorean identity, right? So sine squared x plus cosine squared x equals 1, right? So that's just the Pythagorean identity. Okay. And so we're actually going to start with just cosine and sine. And so there's also a Pythagorean identity for secant and tangent, which we'll get to in a moment. But we're just going to start with cosine and sine to kind of keep it simple. There's also half-angle formulas. And so those look like this. Sine of 2x, so 2 times whatever the angle x happens to be, that's equal to 1 minus cosine squared x over 2. Okay, and this would be the half-angle formula here. There's also the cosine half-angle formula. So the cosine of 2x is equal to 1 plus cosine squared x over 2. So these are half-angle formulas. Right, so these are real handy in trigonometry when you are first learning it, because it allows you to, prove some trig identities or to verify some trig identities. And we're going to use them to, basically convert our integrand into something that, as we said before, kind of has this combination of a nice u with a power rule and then the du kind of in place when you need it. Okay, so the strategy that we'll develop here is based on the odd or evenness of the exponents in the integrand. Okay, so the strategy is based on the oddness or evenness of the exponents on the trig functions. Okay, so there's going to be a handful of kind of principles that we'll use, but they're all going to be based on, is the exponent odd or is it even? So, for example, sine of 2x, sine squared of x, cos x. We'll say cos cubed x. So here we have an even exponent, here we have an odd exponent, right? And so our strategy is going to play on this phenomenon, right? So what trig functions are you looking at, and what's the even-odd structure of the exponents? That's going to be kind of how these work. Okay. So there's a handful of cases that'll emerge, and we're just going to take them one by one and try to intersperse within the cases. We're going to try to do some examples. So the first thing you might see is the following. So if the power of the sine is odd and positive, okay, so odd and positive. So if the power of the sine is odd and positive, what we're going to do is we're going to save one sine factor and convert the remaining factors to cosine. Okay, right, and this is going to play into the idea of our initial motivating example, right? So in our initial example, we had sine to the 5th power, cosine to the 1st power. We use sine as the u, then cosine becomes the du. Right? It's the same thing here. Okay, it's the same idea here. So structurally, what we're thinking here is like the integral of sine to the 2k plus 1, right, of x, times cosine of to the nth power of x. All right, so what we're going to do is so there's an odd number here, 2k plus 1 is an odd exponent. So we're going to write this as sine squared x to the k power times the cosine of x to the nth power, and then times the sine of x dx. So this piece here is what we're going to kind of retain for our du, and then this guy here we're going to convert to cosine using the Pythagorean identity, right? So you would write this like this. So it'd be 1 minus cos squared x to the k power times cos to to the nth power x times sine of x dx. Now everything is cosine, and so when we expand this piece here, we're going to get, some factor times the sine, right? And so whatever happens to be the case with the cosines, we'll always have this sign here that we can use as our du for any u substitution that might emerge. So let's do an example. Let's see how this strategy works in practice. Okay. So let's evaluate the integral of sine cubed x cos to the 4th power x dx. Okay. So notice, of course, in this case, you've got sine raised to the 3rd power, so it's odd and it's positive. So we're going to save one sine factor and convert the remaining factors to cosine. Right, so let's write that down. Save one sine factor and convert the remaining to cosine. Okay, so let's do that. See what that looks like. Let's rewrite this thing down here. Okay, so this would be the integral of sine squared x cos to the 4th x times sine of x dx. So I just basically broke one of those factors off, and I'm going to stick it over here and just leave it alone. So then this sine squared x can be rewritten as 1 minus cosine squared x. Okay, like so. And then there's going to be this part that we're going to kind of expand and rewrite, and then we're always going to retain this sine of x over here for use as part of our u substitution. Okay, so then expanding this, what do we get? We get cosine to the 4th power x minus cosine to the 6th power x. Okay, and that whole thing times sine of x dx. Right, and then we can break it apart if we like, right? So we could write this as the integral of cos to the 4th x sine x dx minus the integral of cos to the 6th x sine x dx. Right, and then we're in a good spot, right? Because we can use u substitutions on both of these. So let's let u equal cos x, then du is equal to negative sine of x dx. Okay, so we get kind of our u substitution here. And so that means we have u to the 4th du, negative, right? And then it's going to be plus u to the 6th du. And so we get negative 1/5 u to the 5th plus 1/7 u to the 7th plus c, and we're just plugging back in u equals cosine. We get the result, right? So negative 1/5 cos 5th x plus 1/7 cos to the 7th x plus c. Okay, so there you have it, right? So convenient, right? When we start up here, it just kind of looks like, oh man, I've got sine raised to the 3rd power, cosine raised to the 4th power. But if you just kind of remember that the goal here is to convert all of them to one of the trig functions, and then just keep one of the other in reserve, right, for your dx, your du. Right, and in this case, that's always easiest if you have sine or cosine raised to an odd positive power, because then you can just take one of them off, and then you can use the Pythagorean identity repeatedly if necessary. Okay, perfect. Great. So that's the idea. That was kind of a straightforward example. Good one to start with. So let's take a look at another example of what can occur. Okay, so another example. Strategy number 2, right? So what if the power of the cosine is odd and positive, right? So if the power of the cosine is odd and positive. Then save one cosine factor and convert the rest to sines. Okay, so basically the reverse of what we just saw. Okay, so structurally it would be something like this. You've got sine of x to the m power times cosine raised to the 2k plus 1 power. Right, we're just going to break off one of those cosines. Right, so it looks like sine raised to the m of x times cos raised to the 2k of x times cos of x. Right, and so this guy right here is going to be the one we hang on to, the one we retain for use as our du. And then we're going to convert this to 1 minus sine squared x. Right, and it's going to be to the kth power. Right, so it might look like this. Sine of x raised to the mth power, and then this will be 1 minus sine squared x to the kth power, and then we still have our cosine over here. Okay, and then just like before, we'd expand this section of it and use this as our du. Okay, let's see an example where this is employed. Now, again, this is very similar to the example that we previously did. So let's work on a slightly harder integral. So what about an integral like this? This would be cosine to the 3rd power of x divided by the square root of sine x. Okay, so this isn't going to be quite as straightforward as the previous example. So again, notice here that the cosine is raised to an odd positive power, so we can employ this strategy number 2. All right, so let's go ahead and do that. So we'll write cos squared x times cos x all over square root of sine x. Okay, and this piece here we can swap in using the Pythagorean identity, we swap some signs in place of the cosine. So that's going to be the integral of 1 minus sine squared x times cos x over the square root of sine x. Okay, and it's probably a good idea to just bring the sign up top here. And so let's see. Well, actually, let's go ahead and distribute first. So we'll have the integral of cos x minus cos x sine squared x over square root of sine x. Okay, and so let's bring the sign up into both of these now. So then when we do that, we'll have integral of cos x, and then it's going to be sine x to the negative 1/2 power minus cos x times, now what happens here? Well, this is sine squared, this is sine to the 1/2, and so what I end up with is sine of x to the 3/2, so like 1.5 you can think of, right? So okay, it looks like that. And let's go ahead and factor out the cosine, and so I get what? Sine of x to the negative 1/2 power minus sine of x to the 3/2 power. Okay, that whole thing times cos x dx. And now I can I can use my u substitution, right? U equals sine of x, du is equal to cos dx. Okay, so I can use that substitution in here, and I get the integral of u to the negative 1/2 minus u to the 3/2 du. Right, so you see the fact that I have this cosine sitting here makes the u substitution straightforward. right? This isn't something you'd probably just stumble into, right? I mean, maybe, but you really kind of have to, I mean, really the main trick here is just taking this cosine cubed and breaking it up right here into these two pieces. And when you do that, it kind of sets the stage for pretty much everything working out. Right, so then we can integrate this and we get, what do we get? U to the 1/2 over 1/2 minus u to the 5/2 over 5/2 plus c. And so we get, let's see, 2 times the square root of u minus 2/5 times u to the 5/2 plus c. And so let's plug back in our sign. And so I get 2 times the square root of sine x minus 2/5 times sine of x to the 5/2 power. All right, there we go. So that is that. So it's similar to the previous example, obviously, and strategically, you know, here we were retaining a copy of cosine. In the previous example, we were retaining a copy of sine, but it's basically the same sort of setup. But this one is a little more involved because you do have some negative exponents. I mean, it's still the same basic integration rule at work, though. Okay, here's another example, the third strategy. So if the powers of both the sine and the cosine are even, if both of them are even and non-negative, we can make repeated use of the half-angle formulas, right? So if both the powers of sine and cosine are even and positive, we can make repeated use of, you know, these guys here. Sine squared x equals 1 minus cos 2x over 2, or, you know, the cosine version. Cosine squared x equals 1 plus cos 2x over 2. And so basically we can use these however many times is necessary to convert the integrand to odd powers of the cosine, and then we can employ the previous strategy 2. So this kind of be like a twofold strategy, right? So first we use these to convert one of the factors, the cosine factors, into having an odd exponent, and then we can employ strategy 2 on top of that. Okay, let's see an example here. Now obviously these can get pretty crazy pretty quickly, so we're going to kind of take a little bit more of a chill one here. So this one is let's evaluate the integral of cosine to the 4th power of x. Right, so here the implication is that sine is raised to the 0 power, which we kind of lump in as the case of the sign being even. So cosine of x raised to the 4th power. Okay, so what we can do is we can use this this identity here. Right, so this would be equal to the integral of cosine squared x squared. Right, and so that means this is going to be the integral of 1 plus cos 2x over 2, and then that whole thing squared, like so. Okay. And, you know, we can expand this, so you get 1/4. Well, if you wanted to do it that way, we'll just write it all as, you know, kind of break out the terms here, but this would be, you know, so 1/2, so it'd be 1/4 plus, and then it would be, in the middle, it'd be cosine of 2x over 2, and then you're going to have the squared term as well, so it'd be cosine squared of 2x over 4, sorry. Okay, so that's how that expands. Right, and so now what can we do? Well, we can just keep going with this one, actually, can't we? We could so this is a squared term here, so we could push this one more time, right? We could write it as 1/4 plus cos 2x over 2 plus, let's see, oh sorry, so this would be like, sorry, I should write it like this, 1/4, and then it'd be cosine squared of 2x, right? So we'll just rewrite it once here like this. Right, so that's just pulling the 4 out, right? So the part that's really important for the substitution is the cosine squared of 2x. That's what matches this format. So we're going to basically plug in another one of these. Okay, so when we do that, we get 1/4 plus cos 2x over 2, right, plus 1/4, and then we have to plug in 1 plus cosine of 4x over 2, okay, like so. Right, and then we can do it, we can just kind of smooth this out, and then everything is just actually the first power. So 1/4 plus cos 2x over 2 plus 1/8, so that's 1/4 times 1/2 plus 1/8 cosine of 4x. Okay, so that gets us all the way out to that. And now we can break this whole integral up. So 1/4 dx plus the integral of cos 2x over 2 dx plus the integral of 1/8 dx plus well, this end one we'll put as 1/8 times the integral of cos 4x dx. All right, so most of these are, well, these two are just constants, so that's not a problem. This one here, we'll just use a simple u substitution. We'll let u equal 2x, then du over 2 equals dx. Okay, so no problem there. And then this one will be similar, right? We'll let u equal 4x, then du over 4 will be equal to dx. Okay, and so kind of working all of that out, running through the numbers here, we get 1/4 x for this guy, and then it's plus 1/4 sine of 2x, right? Because remember this, you've got a half here already, and then you get the du over 2, right? So that's where you get the fourth. And then it's plus 1/8 x. And then here you've got an 8, and the dx is du over 4, so 8 times 4 is 32, so this would be 1 over 32 times the sine of 4x, right? So the integral of cosine is sine. Okay, and then plus c. There you go. So this one was an example where you had an even power on the cosine, and you just had to basically make repeated use of this identity. Okay. Let's see. Yeah, that's good. Let's move on to secant and tangent. So the strategies will be similar. I mean, it's the same idea, but they'll use different. They're going to use different trigonometric identities, mainly different Pythagorean identity, right? So let's see how this looks. So in the first strategy, you would say if the power of the secant is even and positive, okay, save a secant squared factor and convert the remaining to tangent. Okay, and that's because if we use tangent as our u substitute as our u, then secant squared is going to be our du. Okay, so structurally we're kind of looking for integrals that look like this. So secant of x raised to the 2k, okay, times tangent raised to the nth power. So obviously the secant exponent is 2 times k, so it's an even number, right? And so what we're going to do is we're going to hang on to 2 of them. And so here we would have secant squared x, and this will be k minus 1 times tangent n of x, and then we're going to hang on to, we basically took away one of these squared secants. So we're going to hang on to that for our du, and then what we're going to do is we're going to take this and we're going to convert to tangent. And then we want to save this for the du. Okay? Right? So it'll look like this when we kind of do the substitution. So this would be, instead of secant squared, we'll have 1 plus tangent squared. And then we still have this tangent to the n here, and then we're going to hang on to the secant squared at the end. Okay, so this is the substitution that we'll do. Okay, well, sorry, that's the identity that we'll use. Kind of like a substitution, I guess. Okay, so that is the first strategy. Let's just talk through the second case that we'll see as well. So this is when the power of the tangent is odd and positive. Sorry, the previous one was when the secant was even and positive. In the case of this second case, we'll be looking for tangent to be odd and positive. Okay, in that case, we'll want to save a secant tangent factor and convert the rest to secants. So here we want to save a secant tangent factor and convert the rest to secant. Okay, so why are we doing that? Well, because the derivative of secant is secant tangent. Okay, so that's the whole idea here, right? Up top here, the derivative of tangent is secant squared. Sorry, the derivative. So if we can get the integral into this shape, then all of our u's will be tangent. When we differentiate tangent, we get secant squared. So we're going to save this part here for that du factor. Down here, it's different though, right? Like, because first of all, what we're interested in subbing in is u equals secant, and then the derivative of secant is secant tangent, right? So the structure that we're looking for down here is secant to the nth power of x times tangent to the 2k plus 1 power of x dx, right? So tangent is odd. Okay, so we want to retain a secant tangent factor. So that means we're going to have secant to the m minus 1, right? We're going to take one of these, and then we're going to take one of these also. So that means we have a tangent to the 2k x, and then we're going to have left over here secant x tangent x. And that's what we want to hang on to. So this part here we want to save for the du. And what are we going to do with these tangents? Well, we're going to convert all of this to secant. Okay. Okay, so then when we do all of that, it'll look something like this. We'll have a secant of x, that's the m minus 1 power. And then all of these tangents will get converted to secant squared minus 1. So secant squared x minus 1, and that's to the k power. And then we're going to hang on to this thing here for the du. Okay. Right, and then presumably, once we expand this section here, we'll have some kind of a function of secant which hopefully we can convert. We can just use u substitutions in there, and then if u is secant, then du is secant tangent. We'll be ready for that for the u substitution. Okay. All right. Very good. So these two kind of go together, right? It's the same story. It's a little more complicated with secant and tangent because you just have to keep in mind the derivatives aren't like just the opposite, right? So the derivative of tangent is secant squared. The derivative of secant is secant tangent, right? So you have to kind of keep that in mind. Okay, so let's do an example. Let's say we want to evaluate this this integral, tangent of x, tangent cubed x, divided by the square root of secant. Okay, so it looks like this. Okay, so notice tangent is odd. Tan has an odd power. Okay, so that basically means this strategy is what we're going to try to employ, right? So we're going to basically try to retain a secant tangent factor and convert the rest to secant. Okay, so how is this going to work? Well, let's rewrite it with the secant up top. So I have secant of x, negative 1/2 power times tangent cubed of x dx. Okay, so first of all, I can break off one of the tangents. So I have secant x, negative 1/2 power, and now I've got tangent of x squared times tangent of x. Okay, so I've got the tangent part of the secant tangent. Now I need the secant part of the secant tangent. Well, I can just toss in another secant and multiply top and bottom by secant, basically. Right, and if I do that, what do I get? Well, the secant negative 1/2 becomes secant to the negative 3/2. Tangent's unaffected. Right, and then over here I'm going to have a full secant left over. Okay, and that gets me, the piece that I want, right? So this we're gonna save for du. Right, and then what are we going to do? Well, we're going to take all of these and we're going to convert them to secant. Okay, so that's just going to be the Pythagorean identity for secant and tangent. Okay, and so I get, I've still got my secant x to the negative 3/2 power here. And then instead of tangent squared, I'm going to have secant squared x minus 1. And then I've still got my secant x tangent x. Okay, so it looks like that. And then I can, just like before, I can come in here and I can expand this piece of it. Just leave this part alone, but expand this section. Okay, so when I do that, I get, secant to the negative 3/2 times secant squared, and that gets me secant x to the 1/2 power. And then this times that is just the same thing, so minus secant of x to the negative 3/2 power. And then that whole thing is still secant x tan x on the outside there. Okay, now I'm in a good spot, right? Because I can let u equal the secant of x. So then du is equal to secant tangent. Okay, and so the substitution will work out. And I get the integral of u to the 1/2 minus u to the negative 3/2 du. Okay, and so then we can just calculate these using the regular power rule, right? So this would be 2/3 u to the 3/2 minus, and then this will be negative, let's see here, 3/2 plus 1 would be negative 1/2. Yep. So it'll be negative 2u to the negative 1/2. Right, like so. Of course, we got a lot of cleaning up to do here still. So 2/3 u to the 3/2 plus 2u to the negative 1/2 plus c. And so let's toss back in secant. And what do we get? We get 2/3 secant of x to the 3/2 power plus 2 times secant of x to the negative 1/2 power plus c. Okay, so that integral is not too bad. Right, one of the tricks is to not be intimidated when you see, negative exponents in these. So I know a lot of times when I was first learning this, my expectation would be that these rules would be valuable only when I had whole numbers, whole number exponents on these trig functions. And so I would frequently find myself looking for some other way to do this, but it really all that really matters is that one of them be odd or even or whatever the case may be, and the other one can be negative or up, whatever. But so don't be intimidated, into thinking that you can't use this technique just because you maybe have a trig function in the denominator. Right. So the only thing that matters for this strategy is that the tangent has to have an odd power. If that's the case, then you're good to go. Okay. Now there's one other. There's actually two. There's two other cases. There's one other main case that you can come across. If there are no secant factors in the integral, and the tangent is even and positive, what you can do is you can convert a tangent squared factor to a secant squared factor and repeat if necessary. Okay, so let's write that out and then take a look at what that means. So if there are no secant factors, if there are no secant factors, and the power of the tangent is even and positive, you can convert a tan squared factor to a secant squared factor, right? And repeat if necessary. Okay, so it'll look like this, right? Say I have something like tangent to the nth power of x dx, tan to the nth power of x dx. I can write this as the integral of tan of n to the n minus 2 power of x times tan squared x dx. Okay, and what's the benefit there? Well, the benefit is that this is now tan to the n minus 2 of x, and the tangent squared is secant squared minus 1. Okay. Right, and so I can repeat this if necessary to get the integral down to where I can do the u substitution that I'm looking for. Let's see an example here. Actually, do I have an example of this one? Yeah, here's an example. Let's look at this guy, tan to the 4th power of x dx. Okay, so note the power here obviously is even, and there are no secant factors. Okay, so what we're going to do then is we'll just start with this guy and we'll write it as tan squared x times tan squared x dx. Okay, this one can be converted, and we'll have what, secant squared x minus 1. Okay, then we can just do the expansion here. So I get tan squared x secant squared x minus tan squared x dx. All right, and I can just kind of break this apart. should have a dx factor in there for both of those. All right, and then I can do the same thing here. I can expand this one as well. Okay, so let's flip this over here. And so here's where we left off. Integral of tan squared x secant squared x dx minus the integral of tan squared x dx. Now, so what I can do then, what I can do next is, so this part's like really ready to go, right? Because I've got the secant squared here. So if I use tangent as my u, I've got du is secant squared. Over here, though, I don't have that. I don't have it set up for that yet. So I need to do basically the same thing over again. Okay, so let's see what happens here. So we'll hang on to this. And then instead of tangent squared, I'm going to write secant squared x minus 1. So we'll do that. And so this is all just stay the same here. But this guy I can just break apart now. I guess it should be plus, right? Minus, minus, yep. Okay. All right. And so this one here, I need the u sub. U equals tan x. Du equals secant squared x dx. That's for this guy. This one, though, the integral of secant squared is known. It's just tangent. So that's not a problem, right? It's basically the reverse here. You can see that they're antiderivatives, or you can see what the antiderivative there is. And then this is just the integral of dx. Okay, so the whole thing can be done pretty quickly. So let's just rewrite it. So this would be u squared du, right? And this would be minus the integral, I'll just rewrite it. And then this would be plus the integral of dx. And so here this would be 1/3 u to the third power. So I'll just write it since we're kind of learning. I don't want to skip steps. And then this will be minus tan x, and then this will be plus x. Okay, and then let's just lastly kind of toss in the u. So it'll be tan cubed x over 3 minus tan x plus c. Perfect. Okay, so kind of a seemingly really straightforward integral, but there's a little more to it, I guess. You know, it started just like, oh, well, it's tangent raised to the 4th power. Okay, but you're basically trying to maneuver the integrand into something that'll accept u substitutions or just be easily, integrable, sort of like the secant squared here. This is just tangent. We already have an antiderivative there, and so we're good. Okay. All right, so that's a lot of examples. So, I mean, finally, I guess, the other thing to say is that if none of these guidelines work out, if nothing's working, you always can try just converting everything to sine and cosine. But when you're dealing with secant and tangent, it's very possible that by converting everything to sine and cosine, either the sine and cosine rules will apply, or you'll just get like some kind of a convenient, integrand will be the result. So let's do an example there. So let's see something like the integral of secant x over tan squared x. Okay, so notice here that the power, the exponent on secant is odd. It's the first power, right? And so for secant, we're really looking for an even exponent. It doesn't really work if secant is odd. And notice also that the tangent here is negative, right? So for any of these strategies to play out, we really need the tangent. We need the exponents to be positive, right? So none of our strategies will really work for this one. Is there anything else we can do? Well, as I just said, we can try converting everything to sine and cosine. That's really the fourth strategy. I didn't formally state that, but the fourth strategy is to convert secant and tangent to sine and cosine and see if any of the other sine cosine strategies work, or if you just get lucky. So let's see what happens here. So secant is 1 over cos, and tangent is sine over cos. So you get this. And so we can write that as, let's see, this will be cos x over sine squared x. You do get one of the cosines in the bottom to cancel here. Okay. And, well, yeah, so basically this cosine squared comes up to the top, and one of them cancels there, so you're left with just one. Okay. I kind of skipped ahead through that, but hopefully that's not too bad. And so let's rewrite this as the integral of cos x times sine of x to the negative 2 power. And we can see this is gonna work out for us, isn't it? This actually is in perfect state for just a u substitution. Let u equal sine of x, then du is equal to cos x. Okay, and so this would be equal to u to the negative 2 power du. We can integrate that and be u to the negative 1 over negative 1. And so that means this integral is basically negative sine of x to the negative 1 power plus c. And I should have plus c there as well. So this basically becomes negative cosecant of x, doesn't it? All right, perfect. Okay, so that is the basics of, kind of this trick of maneuvering these sine, cosine, secant, tangent combinations into an integrand that you can deal with. Now I know that, when this is presented, it can feel a little like very rigid, a lot of like exponents to remember, a lot of blah blah. I don't recommend that people just like memorize this, like when you're trying to learn this. It's not really, I hate it when people just try to memorize things when they're doing math. Like the idea here is to just expose you to this strategy. Like, oh hey, trig identities can be used in systematic ways to deal with these kinds of combinations of trig functions, right? This is more about just kind of exposing you to that way of thinking. Maybe do a bunch of examples, try to work inside the guidelines. It'll just help you to develop more capabilities in general. So anyways, yeah, I remember when I was taking calculus 2 for the first time, this was very like, this is the kind of thing that I didn't really like. I didn't really like memorizing guidelines like this, but I don't think in the long run, I highly doubt that, professional mathematicians have this sort of thing memorized. I certainly don't. So, if I come across a trig integral, I sort of look into it. And this kind of thing comes back to me very readily as soon as I think of it. But I certainly have to play with it a little bit to make it work. So anyways, that's kind of, I think that's where we'll leave it. That's the end of this. And now in the coming lecture, the next one, we're going to talk a little bit more about trigonometric integrals. And this next lecture will be more about how we can use trigonometry more generally to deal with integrals of a particular form. So it won't be as much like, there won't be as many trig identities and kind of looking at exponents and powers and things like that, but still going to be complicated, but useful as well. So we'll leave it at that, and we'll see you all next time.